Welcome everyone. In this video, I want to put to use some of the work we've done with matrices so far to use perhaps one of the most useful things that we can use with matrices, which is solving systems of linear equations. So let's imagine we have a system of linear equations such as the one that I've got on the screen over here. So here we've got a system of m equations. And each equation has n unknowns, x1, x2, up to xn. So I could write this entire system of linear equations equivalently using matrices down below. And we can see that this matrix equation is equivalent to the system of linear equations above. For example, if I were to multiply this matrix of coefficients with this column vector of x1 up to xn, then matrix multiplication says we take this first row times this column to get the first value in the product. And when I multiply this row and that column, right, we would have a11 times x1 plus a12 times x2 all the way up to a1n times xn. And then we set all of that equal to b1. And we do something similar for every other row, and that gives us a system of equations such as the one that we had above. So I can write this as a system of m different linear equations. I can write that as a matrix as I've done down below, and we can more succinctly write this as a matrix equation AX is equal to B, where A is the matrix of coefficients, X is a column vector of unknowns, and B is a column vector of the right side, the values on the right side of each of these equations. And this matrix equation, AX equals B, this is exactly of the form that we can use the solve function in base R to find a system solution to a matrix equation. So what we enter is the coefficient matrix A on the left side. We enter the column vector of coefficients on the right side and in column vector B. And then when I run this command, it's going to find the column vector X that satisfies this equation. So that's one way that we can solve a system of linear equations using this solve function. And in the special case where the number of equations is equal to the number of unknowns, then m and n are going to equal each other. And this matrix of coefficients A is actually going to be a square matrix. It's going to have the same number of rows and columns. And it's possible that that matrix A can be inverted. And if that's the case, then another way that we can solve this equation, AX equals B, is we can multiply both sides of that equation by the inverse matrix of A inverse. And so on the left side of this equation, the product A inverse A just gives me the identity matrix. And the identity matrix times column vector X is just going to give me column vector X. So when I multiply the left side of this equation by A inverse, it kind of cancels out matrix A, and all that's left is X, this matrix, this column vector of unknowns. And if I multiply the left side by A inverse on the left, I need to do that on the right side as well to preserve this equality. So what I have now, after I multiply this matrix equation by A inverse on the left on both sides, it simplifies to X is equal to A inverse times B. So another way I can solve this equation for X is computing the product of A inverse and B, and that will give me another way of finding the solutions. And that only applies in the special case where A happens to be a square matrix. If A is not a square matrix, then I can use this solve function to try and identify the solution. And we'll take a look at how we can apply both of these methods in the example in the next video.